Hidden inside our walls, there's this incredibly complex web of wires that, well, it powers our entire world. We flip a switch, the lights pop on, and we really don't give it a second thought, do we? But what if the real secret to a safer, more reliable future is actually hiding in that exact technology? Let's pull back the curtain and uncover the unseen science of the modern electrical wire.
I mean, you might think a wire is just a wire, right? Copper, plastic, big deal. But just stop and think about everything you've plugged in today. As our world gets packed with more and more powerful technology, the demands we're putting on our electrical systems have just skyrocketed. So what really separates a basic strand of copper from a cable that's actually built for 21st century safety, that's the big question we're going to dig into.
So, here's our game plan. We'll start with the absolute basics, the anatomy of a wire. Then, we're going to meet the modern safety hero of our story, something called HFEX. From there, we'll investigate two invisible enemies, electrical noise and corrosion. And finally, we'll tie it all together and see why this hidden tech is so incredibly important in our daily lives.
All right, first up, the anatomy of the wire itself. It might look pretty simple from the outside, but trust me, its design is a brilliant piece of multi-layered engineering, and every single layer has a critical job to do. So at its very heart, every modern wire really has three core parts. First, you've got the conductor. That's usually copper, and it's basically the highway for the electricity. Wrapping around that is the insulation, which is the super important safety barrier that keeps the current exactly where it's supposed to be. And then, protecting the whole thing is the outer sheath or jacket. That's the tough shell that guards it from any physical damage.
And here is where the story gets really interesting, because while the copper conductor in the middle hasn't changed all that much over the years, the real revolution in electrical safety has happened in the materials surrounding it, that insulation and the jacket. This is where all the modern science comes into play.
And that revolution in materials brings us to the hero of our story, a modern wiring standard known as HXFIX. It was developed specifically to solve the hidden dangers of older wiring, and it represents a massive, massive leap forward in both safety and performance. Yeah, this comparison right here tells the whole story. For decades, the standard for insulation was PVC. It was cheap, sure, but it had this incredibly dangerous flaw. If it catches fire, it releases this thick, toxic halogen gas. Modern HFX wires, on the other hand, were designed from the ground up to completely eliminate that risk, making them way superior in every key safety metric.
So what does HFix even mean? Well, it's not just a random name. It's a technical breakdown of its benefits. H is for halogen-free. That means no toxic gas. F is for flame retardant, which is pretty self-explanatory. I stands for insulation. And the X? Well, the X is the secret sauce. It stands for cross-linked polyolefin. Just think of cross-linking as strengthening the material's molecular structure, kind of like weaving threads together, which gives it this incredible resistance to heat.
So these features give you three huge real-world advantages. That cross-linked material gives it fantastic heat resistance. Being halogen-free makes it so much safer for people if there's ever a fire. And it's also a lot more flexible, which makes it easier and safer for electricians to install in the first place. Better performance, higher safety, and easier installation, it's a true win-win-win.
Okay, so we've covered heat and fire safety, but there's another invisible threat our wiring has to deal with pretty much all the time: electrical noise.
Just think of electrical noise like the static you hear on an old radio. It's unwanted energy from nearby power lines or other equipment that can disrupt sensitive signals, corrupt your data, or even cause equipment to malfunction. And in a world that is just packed with electronics, this is a huge problem. So engineers developed a kind of armor for the wire, a solution we call shielding. And the process is actually brilliantly simple. It really is like putting armor on the wire. A conductive layer, like a copper braid or some aluminum foil, is wrapped around the core wires. This shield acts like a net, catching all that incoming electrical noise. Then the shield gets connected to a ground wire, which safely drains all that disruptive energy away, leaving the signal inside perfectly clean and protected. And how effective is this? Well, a properly installed and grounded shielded cable can block over 90% of that electrostatic interference. That is literally the difference between a clean, reliable signal and one that's totally corrupted and unusable.
Okay, time for our next invisible enemy: corrosion. But listen, this isn't about rust from rain or anything like that. This is a strange chemical reaction that happens when the wrong metals touch each other, and it slowly degrades the connection until it can become a serious fire hazard.
The technical term for this is galvanic corrosion.
It happens when two different metals, say copper and aluminum, are connected directly to each other. It's like they have a chemical disagreement, and one of the metals just starts to break down or corrode. Now, that weak connection creates resistance, and in any electrical circuit, resistance creates dangerous heat.
So how do engineers fix this problem? With a really clever bit of what you might call metal diplomacy. Instead of connecting copper directly to aluminum, they use a connector that's plated with a third neutral metal, like tin. That tin acts as a compatible bridge between the two, letting the electricity flow smoothly without ever triggering that dangerous corrosive reaction. It's a simple, elegant solution.
All right, we've gone through a lot of technical stuff here, from material science all the way to electrochemistry. But why does any of it actually matter? Let's bring this all back to the real world.
Because this isn't just theory, right? High-performance wiring like HFBX is absolutely essential in places where failure is just not an option. Think about the emergency lights that guide you to safety in a dark parking garage, or the fire alarms that save lives, the massive data centers that run our entire economy, and especially hospitals where reliable power is literally a matter of life and death. In these places, the quality of the wire is a core part of the safety system. And safety isn't just about the wire's material, it's also about the design of the entire circuit. These diagrams show two types of extra-low voltage systems, and both are designed to be safe enough for a person to touch. On the left, you see SLEV, which is totally isolated from the ground. It's like a closed-off little bubble of safe power. On the right, though, is PLEV. It's intentionally connected to the ground so that if anything ever goes wrong, the fault is instantly and safely diverted away.
And you better believe these systems are tested rigorously. This table shows the brutal tests that insulation has to pass. So to make sure a standard 500-volt circuit is safe, it gets zapped with 500 volts of test voltage. But check out the high-voltage systems. They get hit with 1,000 volts. That's double their normal operating load, just to prove that their insulation is absolutely, positively flawless. This isn't just checking a box. It is pushing the system to its absolute limit to guarantee safety. So when you put it all together, it becomes really clear. The quality of the wires that are hidden away in our walls is not some minor detail. It's a foundational piece of modern life. It's the technology that ensures the reliability, the longevity, and above all else, the safety of our homes, our workplaces, and our most critical infrastructure.
We've seen how advancements in material science completely revolutionize something as simple as the electrical wire. It really leaves you wondering, what other piece of invisible, everyday infrastructure is next? What's going to be the H-fix of plumbing, or of data transmission, or even structural supports? It's a pretty exciting thought.